Hi all. Today we discuss theorem 1 of chapter 5 section 2. Last day we have seen how to prove a linear function is a alternating function. That is, we have shown that there is a sufficient condition for getting the n-linear function d as an alternating function. So it is enough to show that uh, d value of the n-linear function d value of matrix a equal to 0 if a contains two equal adjacent rows. So it is enough to prove that condition to get d as a alternating function. In fact, the definition of alternating function is it's an nonlinear function d with d of a equal to 0 whenever a has two equal rows and need not be adjacent anyway. The second statement is the second condition is when we interchange any two rows of a and a prime is obtained by interchanging any two rows of a, then d of a prime is equal to minus of d of a. So these are the two conditions for getting these alternating function. So using this lemmas, we can say that it is enough to show that d satisfies the condition d of a equal to 0 if a has two equal adjacent rows. So using that fact, we will establish the existence of determinant function in any m and k. Now, before that, we have a definition. If n is greater than 1 and A is n by n matrix over K, we let this is just an introduction of the notation Aij. Aij denotes the matrix, the n minus 1 by n minus 1 matrix obtained by deleting ith row and jth column of A. Okay, so this is and that matrix is represented by A of ij. And if D is an n minus 1 linear function, that means the domain of D is mn minus k, that is set of all n minus square matrix of order n minus 1 over the commuted ring with unity k, then this dij of a, this is new notation, dij of a is the d value of, in fact this a is an n by n matrix. So aij, this is a of ij is the matrix obtained by deleting ith row and jth column from A. So this will be an n minus 1 by n minus 1 matrix. So we can apply this d value, because d is n minus 1 linear, d value on this matrix, and that value, that quantity is denoted by dija. Okay? So that is, for example, if we have a 3 by 3 matrix, suppose we have a 3 by 3 matrix, say 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our D. Sorry, this is our A. This A belongs to M3. I take committed unity as R. Then what is A? Or first of all, we define D. D of any matrix A, B, C, D is equal to A times C. Okay, so this is, or I'll write this is AD, anyway, AD minus BC. Okay, so we can get this D is alternating function, and n minus 1 alternating function. D is from this M to R to R. This is our D. Now, this A is a 3 by 3 matrix. It's an element of M3R, and D is n minus 1. That is 3 minus 1 linear function. Then what is D12 of A? So this is what we have put here. Dij of A. D12 of A. D12 of A is D of A12. That is the D value of the matrix obtained from A, deleting the first row of A and the second column of A. Okay, so this is our the matrix is obtained by deleting these two, then we can get the matrix 4, 6, 7, 9, and d value is 36. 36 minus 9 fours are 36, and 6 sevens are 42. So this will be minus 6, right? So this is what we have defined here, dij of a, or d12. For example, d12 of a is obtained from the d value of this matrix, and this matrix is a12 is defined as it is the this is 2 by 2 matrix obtained by deleting first row of a and the second column of a. So then you can get this matrix 4, 6, 7, 9, and find the d value. I have defined d in this manner, ad minus bc, so that is 9 fours minus 6 sevens. Okay, so that will be minus 6. So this is the illustration of this definition. Now we will prove theorem 1. Theorem 1 says that let n greater than or equal greater than 1, and let d be an alternating n minus 1 linear functional on m n minus 1 k, that is set of all matrices of order n minus 1, square matrix of order n minus 1 over a commutative ring unity k. So that d is such n minus 1 linear. Then using this n minus 1 or n minus 1 linear alternating function, we will define, or we will construct an n linear alternating function. Okay, so this d is n minus 1 linear alternating function. Okay, so using this alternating n minus 1 linear function, we will construct this ej. Ej is n linear alternating function. Okay, so using an n minus 1 alternating function, we construct an n linear alternating function. So this is the statement of theorem 1. So how will you construct that n linear? So using this d, we define aij dij of a times this minus 1 power I plus j, and sum up all this. Okay, so I'll illustrate this idea here. If this d is ad minus bc, and if we take a is I'll put it as an arbitrary matrix a11, this is a11, a12, a13. So I'll use the same notation that we have used in theorem 1, that is a11, a12, a13, and a21, a22, a23. The final row is a31, a32, a33. If this is the 3 by 3 matrix, using this two linear, this is in fact two linear alternating function. Using this two linear alternating function, we will construct a 3 linear alternating function. How will you find 3 linear alternating function? So that is using this. First you write E1 of A. What is the definition of E1 of A here? E1 of A is summation I equal to 1, 2, 3. Here we have only 3 rows. Minus 1 power I plus 1. This is I plus j. J is 1 here. Then that is I plus 1. A 1 I is I, and j is 1. A I1 d I1 of A. So this will give your E1 of A. E1 of A is 3 linear alternating function. When you expand this by putting I is equal to 1 first, then you can get this minus 1 raised to 2, that is 1. Then that will be A, I is 1 here, A11 D11 of A, plus A I is 2 here, then A21 D, that is minus. Here I plus 1 is minus here, so minus A21 D21 of A, then plus minus 1 raised to 3 plus 1, that is 1, that is A31 D31 of A. So this is our E1 of A. we need to prove that this is a 3 linear alternating function. If this d is 2 linear alternating function, then we will prove that E1 of A. In the similar fashion, you can define E2 of A and E3 of A by replacing this 1 by 2 and 3. Okay? Then you will get A1, E1, E2, E3. So using 1, 2 linear function or n minus 1 linear alternating function, you can construct more than one n linear alternating function. However, we will later show that these are all the same functions. So there is nothing new about this A2 of A3 of and all. So first of all, we prove using n minus 1 linear, that is 2 linear. Using this 2 linear alternating function, there exists and 3 linear alternating function. So if you apply the induction using 3 linear alternating function, you can construct 4 linear alternating function. So using that, you can construct 5 linear alternating function, and eventually you can get n linear alternating function for every n. Okay, using this fact. Okay, so this is theorem 1 that established the existence of n linear alternating function. Moreover, once you prove this, you can easily infer that if this d is a determinant function, that means 2 linear alternating function with d of I n minus 1 equal to 1, you can get this E1 as determinant function. That is, E1 is a n linear alternative function with E1 of I n is also 1. Okay, so if this d is 2 linear alternating, then Ej are 3 linear alternating. If this d is a determinant function, then this Ej is also a determinant function. So this is what we have stated in theorem 1. Let n greater than or equal to 1 and let d be an alternating n minus 1 linear function on n minus 1 by n minus 1 matrices over K. For each j, j varies from 1 to n, you can construct Ej. Okay, defined by Ej of A is equal to summation I equal to 1 to n minus 1 power I plus j. Aij dij of A is an alternating and linear function on n by n matrices. Okay, if d is determinant function, so is each Ej. Okay, so this is the statement. So we will prove this one. To prove this theorem, we first prove this part is a n linear function. Then after that, we will prove that this is alternating. So first of all, we prove this Aij dij of A is an n linear function. So first we would define f of A is equal to Aij dij of A. Okay, so we'll prove that this is an n linear function. So first we write this A as the rows 1 a1 alpha 1 alpha 2 etc alpha I etc alpha n. We need to prove that when we replace this each row of this A by corresponding C times that row plus that row prime, that is if you have first you take a row which is not equal to the ith row, choose a kth row with k not equal to I, then you define matrix A prime as alpha 1 etc C times alpha k plus alpha k prime etc alpha I etc alpha n. We need to prove that this f is n linear. In this there is a linearity in kth row. This k is not equal to I. So you start with this f of alpha 1 etc C times alpha k plus alpha k prime etc alpha I is there etc alpha n. We need to prove that this is equal to C times f of alpha 1 alpha 2 alpha k etc alpha I etc alpha n plus f of alpha 1 alpha 2 etc alpha k prime etc alpha I etc a n. By definition, this is the value of this is the ijth entry of the matrix A. That means the ijth entry of this matrix. Ijth entry comes from this alpha I, and that is same as Aij. Then dij of the matrix alpha 1 etc. c times alpha k plus alpha k prime etc. alpha I etc. alpha. This is the definition of f. Then this can be written as aij by the definition of dij of this, that is d of the matrix obtained by removing the ith row and jth column of this. So I write that as alpha 1 etc. C times alpha k plus alpha k prime. We remove this ith row. Okay, so that is same as d of this, that is equal to aij times, now you have n minus 1 row in this matrix, then d is we have assumed that d is n minus 1 linear, so you can split or this d has linearity in this kth row. D has linearity in all these n minus 1 rows, in particular it has linearity in this, then you can write that as this quantity as c times d of alpha 1 etc. alpha k etc. alpha n plus d of alpha 1 etc. alpha k prime etc. alpha n. Now you can distribute this aij, that will give c times aij, c times aij into d of alpha 1 etc. alpha k etc. alpha n plus aij times d of alpha 1 etc. alpha k prime etc. alpha n. Now this is same as c times this is same as aij dij of alpha 1 etc. alpha k etc. alpha I etc. alpha n. So dij of this is same as d of this alpha 1 alpha 2 etc. alpha I alpha k etc. alpha n plus this is nothing but aij times dij of alpha 1 etc. alpha k prime etc. alpha n and alpha I is there, then this is equal to, this can be written as c times, this is f of, by definition this is f of alpha 1 alpha 2 etc. alpha k etc. alpha I etc. alpha n plus f of alpha 1 alpha 2 etc. alpha k prime etc. alpha I etc. alpha n. So this shows that this f has linearity in all rows but the ith row. Okay, next we will prove this this f has a linearity in ith row as well. To prove the linearity in the ith row, we write the matrix A prime as alpha 1 etc. We need to change the ith row as alpha I plus alpha I prime etc. alpha n. Then we will prove that f of this alpha 1 etc. c times alpha I plus alpha I prime etc. alpha n. By definition, f of this is the ijth entry of this matrix. Ijth entry comes from this part. This is the ijth entry from ijth entry comes from the ith row. The ith row is this. Then ijth entry is c times aij plus aij prime. So this is the ijth entry of this matrix, and dij of the matrix alpha 1 etc. C times alpha I plus alpha I prime etc. alpha n. Okay, we need to prove that this is same as C times f of alpha 1 alpha 2 alpha I etc. alpha n plus f of alpha 1 alpha 2 etc. alpha I prime etc. alpha n. So by definition this is same as, that is equal to, by the definition of dij, that is same as or you can write this as C times aij plus aij prime times d of, dij of this is same as d of alpha 1 etc. alpha n. We have removed the ith row. Okay, dij of this is same as d of the matrix obtained by removing the ith row and jth column. So from this you remove the ith row. So this is same as C times aij of d of alpha 1 etc alpha n plus aij times aij prime times d of alpha 1 etc alpha n. So this doesn't contain alpha the ith row, and this doesn't contain ith row as well. So you write this is equal to c times aij of dij of d of alpha 1 alpha 2 etc alpha n can be written as dij of alpha 1 etc alpha I etc alpha n. So when you evaluate dij of this, that will be same as d of the matrix obtained by removing the ith row and jth column. So that is same as this one. Similarly, this is same as aij prime d of alpha dij of alpha 1 alpha 2 etc alpha I prime etc alpha n. When you evaluate dij of this, that is same as d of the matrix obtained by removing the ith row and jth column. So that is same as d of alpha 1 alpha 2 etc alpha n. But this is by definition, this is our f of alpha 1 alpha 2 etc alpha I etc alpha n. So that is c times f of alpha 1 etc alpha n alpha I alpha n plus this is by definition, this is the ijth entry of the row I alpha I prime times dij of this. So this is same as f of alpha 1 etc alpha I prime etc alpha n. So which shows that this f has linearity in the row alpha I itself. So this f has linearity in all the n rows. Then this f is a n linear function on m and k. So therefore we can say that this aij dij of a is n linear function. Okay, but we know that the linear combination of n linear functions is again n linear. Therefore this sum, so this is the linear combination of n linear functions aij dij of a. So this is an n linear function. Okay, n linear function. Now we will prove that this eja is alternating. For that we use the sufficient condition that whenever a has two equal adjacent rows, then ej of a equal to 0. So that is enough to get this ej as alternating function. To prove this ej is alternating, we start with a matrix with let be a matrix with two equal adjacent rows. Matrix with two equal adjacent rows. Then we'll prove that ej of a equal to 0. Okay, so if you prove this, you can get this ej as an alternating function. So how will you prove ej of a is equal to 0? By definition, ej of a is same as summation j equal I equal to 1 to n minus 1 power I plus j aij dij of a. Okay, so that means we need to expand this expression when with I equal to 1, I equal to 2 and all. So for I our assumption is this this a has two equal and adjacent rows. Okay, if we say this alpha I equal to alpha I prime, we name that equivalent adjacent rows as ith row and I plus 1th row. Okay, so when you expand this, you can get ej of a equal to the first term will be minus 1 power 1 plus j a1j d1j of a. Okay, plus minus 1 power 2 plus j a to j d to j of a plus etc. plus we have this ith row is there, then minus 1 to the power I plus j aij dij of a. The very next term is minus 1 to the power I plus 1 j I plus 1 plus j I plus 1 plus j times a I plus 1 j d I plus 1 j of a plus etc etc. The last term will be minus 1 to the power n plus j a n j d n j of a. Okay, our assumption is ith row and I plus 1 row are the same. So when you consider the first term of this, in order to evaluate this dij of a, we need to d1j of a, we need to remove the first row. Okay, if you remove the first row, our assumption is ith row and I plus 1 row are the same. So if you remove the first row, still this a has, if you remove the first row of a, then still this a has ith row and I plus 1 row. So this a should have two equal adjacent rows. But we know that this d is n minus 1, this d is n minus 1 linear, and this a has two equal rows, then this value will be 0. Okay, similarly the second term, when you consider d2j, we have to remove the second row and jth column of this, and this still a contains ith row and I plus 1 row, and they are equal. Therefore d2j of a is same as d of the matrix obtained by removing the second row and jth column. Then we have ith column and I plus 1 column in that resultant matrix, and this d is n minus 1 linear, then you can get d of that value 0. That is d2j of a will be 0. Similarly, all the terms will be 0 due to this reason, except for ith row and I plus 1 row. When you remove this ith row, then we cannot expect that this a has ith row and I plus 1 row. So we never get this dij of a will be 0. So we never expect this term is 0 and this term is 0. Rest of the terms are all 0. So the only surviving terms or non-zero terms from this expression is minus 1 to the power I plus j aij dij of a. Okay, plus minus 1 to the power I plus j plus 1 or I plus 1 plus j, that is I plus 1 plus j a I plus 1 j d I plus 1 j of a. Okay, now you observe these matrices. Okay, what is this? This is same as minus 1 to the power I plus j a I j, and this is d of a, removing the ith row and jth column, that is I by j, plus the second term will be minus 1 to the power I plus j plus 1. This will be a I plus 1 j, and this can be written as d of a of I plus 1 by j. Okay, so we have the matrix A with ith row and I plus 1 row are the same. So when you remove from A the ith row, then the resultant matrix obtained by removing the ith row or the I plus 1 row, that resultant matrix will be the same. Okay, that means when you consider a matrix A whose ith row is ai1 ai2 etc ain. Okay, in this matrix the I plus 1 row is the same. Okay, so if you the I plus 1 row can be expressed as the same thing in the ith row, that is I2 etc in. Okay, so this is the ith row and this is the I plus 1 row. Okay, when you remove ith row from this matrix, then you can get a new matrix that is same as obtaining the matrix by removing this. Okay, so we can say that when you remove ith row from A and I plus 1th row from A, then the resultant matrix will be the same. Okay, so we can say that D of A of I by J is same as D of A of I plus 1 by J. Okay, similarly Aij is same as Ai plus 1j, because ith row and I plus 1th row are same for the matrix A. So in effect we can say that these two quantities are the same, since the ith and I plus 1th row of rows of A are equal. Okay, now so these two quantities are same, but this quantity minus 1 raised to I plus j is negative of this one. Okay, so this, if this is the power k, then this is the power k plus 1. There, now you can say that these two quantities are same and opposite sign. Okay, opposite sign here, so that will give the value 0. Now we can say that whenever A has two equal adjacent rows, then Ej of A equal to 0. Consequently, by lemma, Ej of A is alternating. Okay, so whenever D is alternating, n minus 1 linear, D is n minus 1 linear alternating, then you can say that Dj is alternating n linear function. So any n minus 1 linear function induces or generates a n linear function. Okay, now if you assume D of I n minus 1 equal to 1, that means D is n minus 1 alternating determinant function, then you can get Ej's determinant function. Okay, that is because Ej of A is same as, we by definition this is same as summation I equal to 1 to n minus 1 to the power I plus j Aij Dij of A. Okay, then in order to prove this Ej is determinant function, we need to prove that Ej of In is 1. Okay, what is Ej of In? By definition this is summation I equal to 1 to n minus 1 to the power I plus j Aij Dij of In. Okay, but we know that Aij is the ijth entry of this In. The ijth entry of In is delta Ij, so this same as, you can replace this quantity by delta Ij. Okay, so when you expand this summation, the only surviving term is obtained using I equal to j. Okay, in that case we have, that is minus 1 to the power I equal to j, that is 2I, that is same as 1 times, this is delta jj, I is equal to 1 to n, and put I equal to j, that's the only surviving term, that will be 1 again, that is delta jj is 1, and djj of In. Okay, what is djj of In? That is the d value of, that is 1 times d value of INJJ. Okay, so that is, this matrix is obtained by deleting the jth row and jth column of In. Okay, that is obtained by removing the jth column and jth row of nth identity matrix. So when you remove the jth column and jth row of nth identity matrix, you can get n minus 1th identity matrix. Okay, but our assumption is D is determinant function, then D of In is equal to 1, then you can get this is 1. So whenever D of In minus 1 is equal to 1, you can get Ej of In is equal to 1. So this proves the theorem, theorem 1, whenever D is alternating, then D minus Ej is alternating. When D is n linear determinant function, then n minus 1 determinant function, then Ej is a n linear determinant function. Okay, so this proves that theorem, and consequently we have a corollary. Let K be a commutative ring with identity, and let n be positive integer, then there exists at least one determinant function. Okay, that we have already discussed. We already seen that in case of m to k there is a determinant function. So a b c d, then you if this is a, then define d of a as ad minus bc, then this satisfies all the conditions of determinant function. We have already proved in the example that this is alternating and linear, and d of I will be 1 using this formula. So there exists 2 by 2 determinant function. Using this 2 by 2 determinant function, you can by using theorem 1, this 2 by 2 determinant function induces a 3 by 3 determinant function. Okay, so that induces a 4 by 4 determinant function. So there exists, using that argument, we can say that there exists at least one determinant function on any n by n set of all n by n matrices over K. Okay, so these are some examples. Please go through it, and we will later prove that E1 of A, E2 of A, E3 of A are all, if this D is a determinant function, then E1, E2, E3 are all determinant functions. We will prove that the uniqueness of that. Okay, in the next theorem we will show that this E1, E2, E3 are all unique. Okay, in the next session we will discuss that. Okay.